Hi guys, and welcome back to a further discussion of CFD. Today we're going to talk about length scales, and specifically turbulent length scales and the nature of turbulence. And we need to understand a little bit more about turbulence when applying CFD solutions because, as you will find out, it's a very hard problem, specifically computationally, right? And so we need to understand about what is the scope and the nature of turbulence so we can better model it. And then we're going to talk about, eventually, modeling techniques. But this lecture, we're going to focus on the nature of turbulence and the length scales associated with turbulence, this idea called the energy cascade, and then we're going to show that the energy cascade is self-similar. It's also known as the minus 5/3 power law. So let's start here. The Reynolds decomposition. I did some looking around to see when this idea was first put forward, and I don't know exactly. I think it was an idea that wasn't put forward by a single individual, but kind of put forward as a group. And the idea goes like this, that we can decompose turbulent flow into two components, a mean component and a fluctuating component. So here's a turbulent flow over a flat plate, and maybe the external flow is laminar, right? So it's coming in here as a laminar flow. It attaches to the plate, and a boundary layer begins to form, and in so doing, there's a velocity profile. Now, if the Reynolds number is high enough, then within the boundary layer, you can get a transition to turbulence. So here's maybe a slice of that boundary layer through the velocity profile, showing that you've got turbulent flow, eddies and swirls, three-dimensional flow there inside the boundary layer. And eventually, as you get very close to the plate, it must relaminarize and go through that whole transition that we talked about earlier. But within this turbulent region here, if I were to put a hot wire and take a measurement, I might see something like this. So a lot of little fluctuations and maybe an overall change in the mean. So the idea being that I can model this flow by first taking an average, and maybe it's a moving average of the mean flow. So I have an average flow here. The black line is the average flow. And I'm representing the turbulent flow U as the average plus some small fluctuating component or deviation from the average. So ultimately I get something that looks like this, average flow plus fluctuation. So in a way it's kind of a superposition thought, right? That I can decompose this turbulent flow into an average, which maybe is like a laminar flow, plus some fluctuation on top of that. So characterizing the fluctuation is going to be the job of doing turbulent modeling. Let's talk about these fluctuations. When we talk about this flow here, the question is, how big are these little eddies? How big are they relative, say, to the size of the plate L or some other imposed length scale? So Kolmogorov here is kind of gets credit for this idea. Even though the idea was floating around, he really formalized it and came up with this series of scale lengths. Just to give you an idea of what a super genius this guy was, he wrote his first published paper when he was 5 years old. And he recognized in this paper that if you took 1 squared or 2 squared or any integer on down squared, you could actually decompose that into a series of integers or these prime integers here. That's crazy. 5 years old? That is genius. And also, I love these Russian guys from that Cold War era. They're so interesting. Thinking about them toiling away in the snow with not much to work with is really a fun thing to think about. Anyway, Kolmogorov, absolutely a super genius. He introduced the idea that small scales of turbulence are universal. So when you get down in there, when you get down below, say, the kind of the scale length of the large flow, when you get into the turbulent flow, those little swirls and eddies, all turbulence looks the same. And they depend on, the scale rate depends only on the rate of dissipation of turbulence and the kinetic energy per unit mass. Then, as you get down to smaller scale, the scales are dominated by the kinematic viscosity. So let me restate that again. His idea is that you've got a large scale flow like L, and then within that imposed length scale, you might have eddies or swirls on the order of the size L, And then those swirls break into smaller swirls and get smaller and smaller until eventually they're so small that they just instantly go into dissipation via kinematic viscosity. They turn into heat. So the energy that you put in with the mean flow works its way down in scales, making smaller and smaller eddies until eventually the eddies just dissipate into heat and stop swirling. All right, so you got a mean flow. You've got the generation of eddies like we've got here. Big eddies turn little eddies, and little eddies turn even smaller eddies. And eventually this tiniest eddy will just poof, turn into internal energy and heat the local fluid. That's the idea. Here's another picture that I like because this is a fractal. And the thinking now is that this shape, this collection of distribution of scales is fractal in nature. Here's another way to state his idea, that this is a plot of log k, so that's scale length, whoops, that's scale length, and then the y-axis is energy. So you can think of a big eddy turning has more energy maybe than a small eddy turning at the same angular viscosity, angular rate. So energy gets put in at the large scale, and it works its way down through scales, making smaller and smaller scales. As you see here, this big eddy turning smaller and smaller eddies until eventually you get down to the smallest eddies, and those eddies turn instantly into internal energy. So it's a transfer of kinetic energy down through kinetic energy scale and then into internal energy. And the thing that's amazing about what he proposed is this process of big eddies turning little eddies all happens inviscidly. So there's no loss of energy to viscosity, which is an irreversible process, until you get down to the smallest scale, which today we call that the Kolmogorov scale. So you get a mean flow like this, and maybe the mean flow is, like this is showing flow over a circular cylinder, so you get a mean flow coming in, and then you've got some imposed length scale, L, maybe it's the size of the cylinder. And in this case, you're saying, okay, you're generating vorticity or eddies at the size L, so that looks to be true. Maybe like this big eddy right here is kind of on the size of this diameter of the cylinder. And then those generate smaller eddies and smaller still eddies, and you can imagine this is swirling out there as it goes down, breaking up into smaller and smaller eddies, but all that's happening invisibly. And then finally, when you get down to the Kolmogorov scale, which we're going to call eta, you get down to that scale, it goes right from eta, from this tiny swirl, right to internal energy and heating. So that's what happens here. The energy is passed from scale to scale, and then right into, finally, into heat. So if this is the idea, let's do a little dimensional analysis. Let's do kind of a simple Buckingham pie. Let's think about the kinetic energy at the large scale. This is kind of the input energy into our system. So the only parameters we can use are L and the velocity, some root mean square velocity, some kind of averagey velocity that is characteristic of the system. And L is this imposed length scale at the large scale. So if I just try to make a function or rearrange these in order to get kinetic energy per unit mass, it's pretty easy to do, right? Kinetic energy is 1/2 mass velocity squared, and then per unit mass, I divide by another mass, I get just the RMS squared, which is kind of representative of the input kinetic energy into the system. The other scale that we need to know is this dissipation through the scales. So this is not dissipation, molecular dissipation into heat like viscosity, but this process of breaking big eddies into smaller eddies, so this kind of dissipative process. And again, I can't use viscosity here as a parameter because I'm reserving that for after they're broken down and you get to the smallest scale, then viscosity takes over and dissipates the energy. So the dissipation through scales has to occur just using these large scale sort of quantities. So again, F and the RMS velocity. So if I arrange this to have units of dissipation, right, and units of dissipation in this case are like m squared over seconds, right, this is this nu, then to get those units would be velocity cubed divided by L. And that would give me the right units, right? So it's just a time scale here times this dissipation rate. So that's a really fascinating non-dimensionalization. Let's go for the smallest scales. Now, at the smallest scales, we're saying, hey, viscosity is a player. The energy is coming from this dissipation rate here, and it's being deposited into internal energy or viscosity. So can I come up with a scale length eta using just those two parameters? And of course, I can. That's called the Kolmogorov length scale. So if you just do a dimensional analysis, you'll get the viscosity nu cubed divided by the dissipation rate raised to the 1/4 power. I can form a Kolmogorov time scale. So this is how fast does it take for the energy at this small scale to be dissipated. And then finally, I could come up with a velocity scale. Kind of what's the velocity at this small scale? So the fascinating thing about this is that these scales are larger than the continuum scale, larger by quite a bit, actually. So that's great because remember, all of fluid mechanics sits on top of this idea that we're not dealing with a collection of molecules. Well, I shouldn't say all of fluid mechanics. All of continuum fluid mechanics sits on this idea that we're not dealing with a collection of molecules, but in fact we're dealing with some sort of continuous medium, which doesn't really exist, right? Air is composed of small molecules, but this Kolmogorov scale is much, much, much larger than the scale of the molecule itself. So it is in the continuum, thank goodness, because imagine if this turbulence took us below the continuum such that it affected what was happening at the molecular scale. Oh, what a hard problem this would be. All right, so here's the real proof in Kolmogorov's idea. His idea is that this process of big eddies to smaller still, all of this turning of gears is happening inviscidly or reversibly, so there's no friction in the gears, so to speak. And then only when you get down to the smallest scales does the energy get absorbed into internal energy via viscous interactions. So what we find is by taking data is that it is true that all of this is our cascade right here. This is this inviscid process, and all data falls onto a single curve all the way down to the smallest eddies. So these are eddy sizes here and basically energy on the y-axis. And look at the data. This is taken in things like tidal channels. So you can go look at data as ocean waves as these waves move into these large fjords, or meteorological data where you have towers with hot wire anemometers on them. And the reason we look at these super large fluid flows is because we can really get in there with the scales. You know, if you did this in a wind tunnel, the Kolmogorov scale might be so tiny that it's smaller than the hot wire, so you can't make a measurement of the Kolmogorov scale. But if we look at really large turbulent flows, like meteorological scale turbulent flows, we have a chance of actually making measurements all the way down to the Kolmogorov scale. So these are a collection of flows. Some of them are homogeneous shear flow or wake behind a circular cylinder, so they might be large experiments. Grid turbulence, that was really pioneered by G.I. Taylor. But yeah, any flow you can think of. The fascinating thing is that eventually this distribution of scales within the turbulence, this kind of medium scale here is self-similar. It is irrespective of what's happening at the large scale. Think about what that means. All turbulence is self-similar. So that means if I have a flow, like flow over a flat plate, and I zoom in and I look at just a little section of that flow, I can't really tell if those swirls and that formulation and that passing of energy through the dissipation range, is that coming from flow over a flat plate or flow behind a circular cylinder or airflow in the atmosphere. At some scale, over some huge scale length, all flows become self-similar. All turbulent flows become self-similar. So this is a way to grab a hold of turbulence here. And this basic roll-off of energy is the -5/3 law, that they all kind of fall on to some curve, a -5/3 curve. Now this is plotted log here, but that's the general idea. That is crazy awesome, right? Thank you, Kolmogorov. So I think that this collection of scales is built into our psyche, the way we look at flows. Like when we see Godzilla moving through water, or we see him moving, we're like, oh man, that looks fake. It's because it's not following this length scale that we're kind of used to seeing. We expect to see a distribution of length scales, and from that we expect, or that's what we recognize as turbulent flows. So when we see a flow like here's water emitting into a pool and it's creating this kind of turbulent flow, and we look in there and we begin to see scales, right? Here's a drawing by Da Vinci kind of illustrating what I'm talking about. Da Vinci was no fool, right? Here's the water coming in, and this is a tidal pool. This isn't just chaos. He's drawing scales, very obvious scales. Distribution of scales is what he's drawing, right? So there's a scale length associated to this flow coming in. Maybe it's this lambda naught. But in general, there's a large scale. So how big is this scale relative to that scale, right? We would expect it not to be, we would expect it to be a certain kind of parametric relationship there. And then what about this sort of large jetting out structure, or smaller and smaller scales as we go down to these kinds of eddies here, like this guy right here, and even smaller scales still. So think about the energy cascade, and what that's telling us is there's a distribution of scales, and all turbulence follows the same distribution of scales. What a powerful idea. Remember Louis Richardson here, this guy from the Richardson number? He had this little poem that he wrote. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. That's the whole thing right there. Big swirls, energy from the big whirls, have little whirls that feed on their velocity, right? They're driven by these inertial processes, these inviscid inertial processes. And then little whirls have even smaller whirls, and so on as you go down the scale all the way till you get to the final resting home, which is viscous dissipation. What a great poem, right? I learned that that's actually a rip from Jonathan Swift, right? So naturalists observe, a flea hath smaller fleas that on him prey, and these have smaller fleas to bite them and protect them, and so proceeds ad infinitum. That almost rhymed. But yeah, basically, it's the horse has a who sort of idea that there's this distribution of scales right on down. Pretty cool. Anyway, thank you, Da Vinci and Komagora, for this super neat idea about the distribution of scales and turbulence. See you next time.